A very good morning, everyone. Welcome to yet another edition of the Guest Talk series organized by the Astronomical Society of the University of Peradeniya. Today's talk is centered on the theme of modern radio astronomy, and I take this opportunity to introduce and welcome our esteemed guest speaker, Dr. Sarod Yatawatta. Uh, Dr. Yatawatta obtained his Bachelor of Science degree in Electrical and Electronic Engineering from the University of Peradeniya, Sri Lanka, in the year 2000. And he pursued his PhD degree in Electrical Engineering from Drexel University of Engineering in Philadelphia. And thereafter, he moved to the Netherlands, where he is currently a research scientist at the Netherlands Institute of Radio Astronomy, ASTRON, developing algorithms and techniques for next generation radio telescopes. His research interests include signal processing, scientific computing, and machine learning. And without further ado, sir, the stage is yours. Thank you.
Thank you for the invitation. Yeah, so I'll just show my face just for a moment. If you haven't seen me. Yeah, it's good to also have a nice crowd, especially after this the weather problems that we all know about. But it's good to get things back to normal and see you all back to the learning process. So without further ado, let me go to this talk is about modern radio astronomy. So I'm not sure what the background of each of you are. So I just give you a highlight. Just a broad and also just an up-to-date overview of radio astronomy. I'll provide you an introduction to radio astronomy, basic and also some of the techniques, especially the interferometric techniques, and also just give you an outline of what is happening in the world in the latest um, developments and research in radio astronomy. I'm focusing more on the concepts rather than on facts like what is the speed of light, things like that. Those are facts. But I just want you to understand more the more of the concepts than the facts that I state in this presentation. Okay, what is radio astronomy? So here I have shown you three images. One of them is made by a radio telescope. So I'm not sure whether you can guess which one that is. But two of them are made by other telescopes that are using other techniques. But one is made by radio astronomy, radio interferometry. So just to be more specific, I think the one in the middle is the one. This one is the one made with radio astronomy, radio telescopes, and the one on the left and the right, they are just Hubble or James Webb telescope images. You can see that the electromagnetic spectrum is a very it varies from it goes from the lowest frequency to highest frequency range, or conversely from the lowest wavelength, smallest wavelength, to the highest wavelength. So here you see the full spectrum that we in nature that we encounter. On the right hand side you have the lowest frequency, so the longest wavelengths, and on the left hand side you see the highest frequencies and also the smallest wavelengths. So the thing to note about is this equation on the left hand side, energy is proportional to the frequency. energy of the radiation. And you can see also the middle, the visible spectrum. So that's, you can see it's a very narrow. If you look at the radio, on the right hand side, the visible spectrum was a very narrow spectrum. So the available frequency range uh, for radio is much broader than an optical. So that's what we see using our own eyes, and also compared to other bands. Other methods of observing like gamma, you can see that by comparison, the bandwidth is larger. Going to next slide. What do we observe especially in radio astronomy? So obviously we need to have some kind of a source that emits radiation, or it can be also reflections, but or reflections itself need some kind of a source of radiation. So we can divide the types of radiation into these categories as thermal and also non-thermal. And you can see that because the origins are different. If you look at the right-hand image, you can see that what we see in radio is significantly different than what we see using optical telescopes. The reason is, yeah, obviously the way the physics behind each of the radiation emissions are different, and also how they are distributed is also different. Because of that, yeah, we can see a different. So this is actually the galaxy. You can see a different structure in the galaxy compared to the optical than in the radio. When did the radio when did we started using radio frequency ranges for observing the sky? So actually, the first detection using radio frequencies was done by Jansky. Because of that, we name the flux measurement unit as Jansky also, instead of the conventional SI units. In radio astronomy, we have a special unit called Jansky. So this was done in the 1930s. He was an engineer measuring working with some uh, electrical equipment, and he was always receiving some kind of a or noise-like source, and it turned out to be the radiation that is emitted by the galaxy. So that's what he discovered in the 1930s. And this work was continued on by others like Rode. So he was actually an amateur astronomer, so he did not have any technical or educational background in radio astronomy, unlike Jansky, who was an engineer. But he was just very enthusiastic. He built the telescopes, a dish like this, in his backyard, and he did some experimentations, and he was able to plot the intensity of the emission that was detected by Jansky in the sky. So technically speaking, he made the first radio map of the sky. Right now, we have much more advanced ways of imaging the sky, which I will describe later. But this technique was first described in the 1940s, and also this was developed in the 1960s. So it is called the aperture synthesis. So this is an inherent technique in radio interferometry. I just want to point out that in an optical telescope, we just point the telescope to what we want to look, and we see that we make an image. But in radio interferometry, we do not have that luxury. We have to use other techniques to make the image. So that's the major difference in radio interferometry. So to sum up, these are the fundamental properties of radio telescopes. yeah, uh, we have the radio telescopes are very sensitive to very weak signals, and we can increase the resolution. But also building a radio telescope compared to, for instance, an optical telescope is very expensive, a large radio telescope. But we can break down, we can assemble small components, hardware or antennas to build a large radio telescope. I will show you some examples later. So here are some different examples of radio telescopes. Um, on the top row, on the left to right, you can see that this is actually the sky, I mean the bird's eye view of a telescope on in the Netherlands. In the middle panel, this one is actually a telescope that is being built in Australia. And on the right hand side is an extreme case. This is a telescope that is in space. So this is actually a satellite acting as a radio telescope. So these are actually, you can see that if you look closely, these are just some wires. So this is very inexpensive components acting together to build the telescope like a dish. So on the bottom row, you can see what you conventional telescopes we think of as a radio telescope. So this is actually a satellite dish, a very big one. But building this kind of a dish is very expensive compared to the ones that like the top row have shown. So the principal concept is, yeah, by assembling smaller and cheaper components, you can build larger telescopes. Here is a close-up example. So this is again a telescope in the Netherlands. This has, you can see the dishes. You can see also for scale, you can see the normal building sizes. So you can guess how big they are. So this is actually a radio telescope that is 14 dishes that are on a straight line. So this is actually uh, one of the oldest radio telescopes on Earth. So this is very old technology, but we still it's being used for some science. In contrast, this is a new telescope. This is again a bird's eye view. For scale, you can see the small box-like things. Those are actually a size of a refrigerator, or a compute cabinet. So you can estimate what the scale of this thing is. These boxes like things that are on the ground, so they are inside them. We have antennas and wires, etc., etc. Again, these things that are spread out on the ground, they are also different kinds of antennas. Here you can see on the right-hand side how they are made up of. So, for instance, this is again a field of antennas. These antennas are sensitive to, for instance, here we measure the frequency range from 10 to 90 megahertz. And the black boxes that are on the ground, so these antennas are sensitive from 110 to 240. So it's a slightly higher frequency range. From 90 to 110, we do not observe because that's the band that we use for FM radio transmission. And also, you can see that the lowest frequency here is 10. So going below 10 is not possible because of the Earth's atmosphere will block out all the radiation coming from the sky. So that's called the cutoff frequency of radio waves. And because of that, of course, whatever we transmit below this frequency range will also get bounced off the atmosphere or the ionosphere. And that's how for instance, the short-wave radio transmissions operate. So this, you can see that they are very simple and cheap hardware, but there are thousands of this hardware that are combined to build to act as a large telescope. Again, going back to this same telescope, which is called LOFA. So the one I showed you is at this center of this on this image. But we have also, yeah, receivers all spread all over Europe. So The reason for having this kind of uh, far far apart receivers is to increase the resolution of images. So I will describe that in a later slide. The one that is being built, another telescope, even bigger telescope, is being built right now in Australia, also in South Africa. Again, you can see that some antennas are like this. These are just wires, and also you can see some dishes. So the dishes are ideal for higher frequencies. So the wire-like antenna are suitable for the low frequencies from 10 to 200 megahertz. So the ones in the dishes are gigahertz range receivers. So those are the kind of hardware that is being used right now, and being developed. Of course, you can see the hardware is pretty much simple, but because of this, we have to pay a price in terms of the data processing. I will explain that in the coming slides. We use simple hardware, cheaper to mass produce, but we get what we get as data. We have to do a lot of processing. So in order to go into the data processing, so I hope all of you know what a Fourier transform is. Here I show on the left-hand side an image. This is actually a source of a radio source. And on the right-hand side is the Fourier transform of this image. So in radio interferometry, what we observe is actually the right-hand side. In an optical telescope, what we observe is actually the image itself, but in radio interferometry, we observe the right-hand side. Okay, so to go into a bit more details, how this is the most fundamental concept in radio interferometry that I want you to understand. We have two of these antennas here in this image. This one and this. So they are looking at this. These are the beams. They are looking at the sky. So this is the sky, and we get the signal, and we do a correlation here. So this is a correlator. So correlation means we get two signals from these two receivers, and then we multiply them and add them together. So if we do it like this, we can show that mathematically what we get as the correlation as on the left-hand side is output. It's actually the Fourier transform of this the actual sky, the Fourier transform, so two-dimensional Fourier transform. So this is a very basic principle of radio interferometry. Because of this, we observe this, and we take the inverse Fourier transform to get this. So that's pretty much how a radio telescope, radio interferometer operates. A very basic description. Of course, there are many complex fine detail you have to take in to consider. And this is called the van Sittert-Zernike theorem. So that's the basic building block of radio interferometry. I just want to clear up all these things I drew. Okay, so we observe the Fourier transform. So in the Fourier transform, we don't have the full information of all the Fourier space samples. So if you filling, so this is the left-hand side is what we observe as in a radio telescope. You can see that there's a lot of empty points. So we don't have that information because we have a fixed set of receivers. Here we have a set of fixed locations of these receivers. So we can't fill all over the place with these receivers because that's a cost limitation. Because of that, what we observe in the Fourier space also has empty spaces. If we have too many empty spaces, when we get the inverse Fourier transform, we get a poor quality image. That is the one in the middle here. So the right hand side, the left, the the mid panel on the right-hand side, you can see that it's not a very good image. But if we can fill up all the empty spaces on the Fourier space, you can get a better image. That is what we see on the right-hand side. So this can be done because if you keep these two antennas on Earth, and as the Earth is rotates, because we know that the Earth rotates, the relative location of these two uh, receivers changes. And because of that, the points on this Fourier space also changes. That's why actually we have these circular patterns. That's because of the Earth rotation. So using Earth rotation, we can fill up the empty Fourier space to get a uh, better image. Of course, this again not 100% complete. Uh, Even the final image, we have what we call as a point spread function. So if you image a point, what we actually create using radio astronomy is not actually a point. It's just a blurred out or broadened point. So that's called the point spread function. So we need to deconvolve. So that's again an additional processing step to get the best quality image from this kind of images. Uh, okay, so I see a comment about the options bar. Let me just uh, I'm not sure how can I move this. Do you see it now?
So it's all right now.
Yeah, I'm not sure. I should be able to hide this also. If you have any questions, of course, you can also shout on, I'll keep it like this. Okay, so that's the basic concept of imaging in radio astronomy. So that you can see that clearly that this is much different than an optical telescope. You point it to a star or something on the sky, and then you look at it. But this is not like that. It's much more involved. And because of that, there's a lot of processing steps that need to happen. So for instance, I moved here. This I have listed here 4 fundamental processing steps that must happen in any radio astronomical processing, because we get the data, like we get the samples from in the Fourier space, but we need to clean this data because your mobile phones, the satellites, your all the electronic equipment, they also create radiation, electromagnetic radiation. So those also will be picked up by your radio telescope. So because of that, they act as interference that makes the data not usable because of that. So we have to remove all those interfering signals from your data. So that's the first step to do. And then we have errors in your hardware. So we have to correct for those systematic errors. So that's the second step. And then the third step is the image synthesis. That's what like I showed in the previous slide. You have your Fourier space data. You have to take the inverse Fourier transform, and also you have to do some deconvolution to fill out the empty spaces, etc., etc. And after all these things have been done, on the final step, you get an image that where you can do some science. You can um, detect a new planet or detect some changes in your some kind of a star or whatever, something like that. So you can see that there's a lot of processing that has to happen before any science can be attempted in this kind of data. So this is actually a very rough schematic on the bottom. You can see that you get a lot of data, and then you do a lot of processing stuff. You also store the data, and then you can do offline stored data processing, and then you can extract various science results after processing the data. So this again, what is unique in radio interferometry compared to any other discipline? So there are very different as you can see, have seen, the imaging process itself is unique. And because of that also, and also because of the sensitivity or the attenuation of radio waves, even when for instance in daylight, we can get data in the sky. So we can observe even regardless of day or night. We can observe also full polarization. So that's again a fine point. We have electromagnetic radiation. They will have also some kind of polarization information. So that's how the electromagnetic radiation behaves in the three-dimensional space, uh, orthogonal to how it is being propagated. So that's I won't touch into that. We can increase the resolution. So for instance, I have shown here the black hole image. So this, in order to build this, make this image, you have to build if you imagine, if you want to look at this black hole using an optical telescope, you have to build a telescope that is big as the Earth. So that is impossible, right? But with radio interferometry, we can place antennas, for instance, in one in the North Pole or in the one in the South Pole. So we can get the same kind of resolution as building yeah, building a telescope as the size of the Earth. So that's very rough explanation, but we have much higher resolution in radio interferometry than in any other band of radio, any other band of astronomical telescopes. And also I mentioned that we have very large bandwidth from going from tens of megahertz to even to several gigahertz. So within all that the bandwidth, we can do a lot of observations, and we can study the changes in physical processes with frequency, for instance, and like that. So we have freedom to do that. And the other important thing is we can get data for a long period, sometimes days, sometimes years. So people, yeah, even decades, we can collect data because the sky is pretty much stable. It does nothing much changes. Because of that, we can continue observing the same part of the sky, and because with this we can beat down noise. So to ask your question, can we do the same? Like for instance, if you want to make a image using take a photo using your mobile phone, can we keep the photo making a? I mean, can we keep taking more and more photos of the same thing and then add them up, hoping that we get a better image? Normally, it does not work because in that case, the noise is not not Gaussian, and also the image is not limited by the noise. It's limited by the in your mobile phone. You have the camera has a pixelized sensor, so the number of pixels. So even though you can keep pointing your camera to an object for days, you will not get any better image than just taking 1 second to make an image. But in a radio telescope, it's different. You can indeed get much better results. Because of that, of course, you can accumulate a lot of large amounts of data, uh, which I will describe in following slide. And also, I just want to point out, so some of the techniques have applications outside radio astronomy. For instance, the imaging concepts that is very much related to MRI, so medical imaging, and also things. Some of the other things, techniques that I use in radio interferometry can be used by wireless Wi-Fi data, like Wi-Fi transmission, source location, etc. So there's a lot of cross application technology that is used in radio interferometry. So going back to the data, so because we can accumulate many days or nights, we are always yeah we are always flooded with data. I don't want to bring up the flooding part, but that is what we exactly feel in this if you have a astronomy, if you work in this field. So we even with you can see this. I have given some of the data rates here, also the data volume that we need to store. So this yeah, this is unprecedented. So I don't think any other application can produce this amount of data and this amount of data in a very fast time period. So because of that, we have to the modern astronomy part. The modern part comes. Yeah, we have to think about how to process this data, not only to get the best result, and also we have to think about the carbon footprint. Cannot spend too much energy, etc. Things like that. We have to think about the environment. So things like that. So that's where we are moving towards. One important aspect of data processing is calibration. So calibration I mentioned is correcting for the systematic errors. We have a lot of errors because we use a lot of cheaper hardware, not very precise fine-tuned hardware because we have thousands of receivers, thousands of antennas, etc. So they have their own errors. So those kind of errors need to be determined, and also the corrected for the data has to be corrected for that kind of errors. So that is called calibration. That is again combine this kind of errors with the high data rate. So this has to be done very fast and also in very accurate manner. Here I showed on the bottom two images. So the one on the left is without calibration, and the one on the right is with calibration. You can see the difference between the. So most of this structure on the left you see are due to the systematic errors in the data. And so this has to be done in a very fast way because we have a lot of data to process. So one thing we can easily run into is, yeah, we try to calibrate something and we expect something like this top panel here, but what we can get something completely different. We don't know that. So we have to be very careful. So many things can go wrong, things like this. So we have to do a lot of checking. Like you can use a lot of tools like AI or statistics, things like that to get to do this accurately and also to do this fast. So that's again because dealing with large amounts of data, we have to develop techniques that that can self-correct and self-diagnose what is happening, things like that. So for that kind of things, we use AI. The future of radio astronomy. So I mentioned that we have a lot of data. Need to handle a lot of data. Uh, we also right now we are faced with a lot of satellites on the in the sky. A lot of satellites by, for instance, for internet. So this is very sudden. So this is a very rapid increase of the interference caused by things like that. So because of that, some people are even considering building a radio telescope on the moon, the far side, because there will not get corruptions from man-made interference. And the other thing is, yeah, we need to be sustainable. So we have to think about the world, the earth, uh, to reduce the energy consumption, carbon footprint, etc. So with all this, there's a lot of science that can be done in using radio astronomy. Here I have shown, I have listed the few. We can, uh, yeah, we can do science in the past. I will explain that in the following slide. From past to present, so we can look back into time, and also from past to present, and also from near to far. So, for instance, we can use techniques in radio astronomy to study lightning or asteroids, even planes that are travel in the sky. The radiation from the sun gets reflected from the planes, so we can track things like that. we can of course study the our own sun and all the planets, and not, but we can go beyond that. We can try to detect extraterrestrial signals, so aliens, and also fundamental physics like gravitational waves, also new life like exoplanets, and also cosmology, so the history and all the also the fundamental theories like the relativity, etc., verifying those kind of theories. So there's a lot of broad uh, science course that can be that are done being done by this kind of technological developments. One thing I had to highlight is the going back to the past. So the two things you have to consider that we know that probably you have heard that the universe is an established fact that the universe is expanding, and but the speed of the travel speed of light or the photons is finite. So because of that, things that happened in the past, how redshift, that means the radiation, is what we observe that has happened in the past. If we observe them now, they will have redshift. So that means the frequency of the observation will be lower than what is original. So because of that, yeah, we can, because using this technique, we can look back into time, and also going back to the just after the Big Bang. So this is again a very uh, hot area of research using radio astronomy. Conclusions, yeah. As I showed you previously, you have radio astronomy has very distinct characteristics that makes it unique compared to other observing uh, bands like the optical or infrared, etc., etc. And also, yeah, there's a lot of new radio telescopes that are being built on Earth, and also in uh, being planned in other uh, planets. We are dealing with a lot of increasing amounts of data, but we have to be we are careful. We have to do some intelligent way of processing the data. Um, not only not only just getting the correct result, but also using uh, our resources on Earth in a efficient manner. Okay, so that's all I had to say. I can now stop and ask if you have any questions.
Most profoundly delighted to about that. And now we move into the Q&A session. And anyone who has questions can are welcome to unmute and ask any question from our guest speaker. Or else you can also direct your question via the chat box. Okay, now it's time for the questions. Uh, in the meanwhile, sir, I do have a personal question. So, if we are considering the radio data, is there a method to like differentiate between thermal and non-thermal radio waves, so that we can like say that if it's a black hole or if it's a pulsar or a neutron star? So, is there a method?
Yeah, because we can use the frequency information, right? So that the how the spectrum the radiation changes, the spectral indices, etc. Because of that, we can distinguish between that kind of things.
So, if there are any questions, you can direct it towards the Q&A as well. Okay, there's a question, sir, if you can view it. Uh, okay, so there's a question about, sir, when we receive signals through radio telescopes and after going through the amplifiers and filters, what kind of data do we record in the computer?
Okay, yeah. So first of all, we get let's say we select one data stream. We digitize that data, so it's analog, right? We get the antenna. We have a low uh, low noise amplifier at the antenna, and then we measure that, and we digitize that to make a value that is a floating point value. Okay, and then we use polyphase channelizer. I'm not sure whether you know about that. So we split that data into very narrow band channels. So because we get the full bandwidth for information. So that is after that is fed to a correlator where the correlator multiplies that data with another data coming from a different receiver. So that is the data that is actually being stored on this. So that can be for imaging. I also did not mention that we can also record data for time series observations like transients, transient signature, etc., things like that. So again, that's recorded as a time series.
And sir, I would like to also add another question, like in noise mitigation, is it solely done using computational means? So can we use like hardware components like RF filters and other sort of methods as well?
Yeah, we have to. For instance, we need to use good low noise amplifiers and some of the frequencies. For instance, for the higher gigahertz range, we have also cooling at of the hardware. But right now, we also at Astron we also work with room temperature, ambient temperature receivers that work equally well. But normally, the higher frequency receivers we have cooling, so that's and also shielding and using, for instance, the fact that we use a dish is to concentrate the radiation to beat the noise.
We do have another question, sir. If you can believe it. Collecting data during the daytime and nighttime, how does the solar radiation interfere with the data collected?
Well, indeed, the solar radiation does interfere with your data, but that is again a separate source. For instance, even if you observe at night, there are equally bright radio sources in the sky, like Cassiopeia A, Cygnus A, things like that. They're equally bright as the sun. So regardless of whether we observe at day or night, we have to deal with those kind of sources. So that's not a real problem. We can subtract that signal. So that's what I wanted to say. The
Also
sun
in
signal from the
image,
sun.
also say
Sorry.
in image enhancement, do we use neural networks as of now for image processing techniques?
Yeah. Well, there are various ways of using neural networks and AI. So not only for image enhancement, but yeah, many things. Yeah. So, but in principle, yeah, uh, we do use things like neural networks.
If anyone has any more questions, we can please do unmute and or direct your question to the chat box.
Actually, what's the progress in the radio astronomy in Sri Lanka universities and this and that?
I'm not sure I don't really think there's actually a program dedicated for radio astronomy, but as I mentioned in the talk, most of the radio astronomical fundamentals are related to radar uh, or wireless. So the basic techniques can be learned by, for instance, in an engineering degree, can be an elective subject.
Also, sir, we got a question regarding the higher education aspects in this field, and also what sort of a basic degree or what sort of background knowledge that one should have to pursue this field.
Uh, well, I don't think that's for somebody who wants to do a postgraduate uh, study in this field. Uh, if you are familiar with mathematics and fundamental physics, so those are the only basic requirements. Uh, that's nothing different than uh, any other study that requirement for any other study, like any other physics or mathematics based study.
Regarding this inverse Fourier transform, it's just a it's about mathematics here. So the function I that we get from the inverse Fourier transform on the correlations, is it the intensity of the signal that we get?
Uh, uh, it's actually the correlation is actually a complex number, right? So you have the amplitude and the phase. So if you do an inverse Fourier transform, you get also a real and imaginary part. But we know if you look at the sky, it's a real part, right? So the inverse Fourier transform mathematically, ideally the imaginary part of the inverse Fourier transform should be zero because the sky has only a intensity, right? But due to numerical errors, etc., imaginary part will have a very small value, but we throw away that one actually.
We got another question from the Q&A session. So, if we have one telescope that is sensitive to H1 line, hydrogen line,
Yeah.
and can we use that telescope to plot the galactic rotation curve? Yes, the received data is flux versus frequency.
Yeah, I think so. That's how normally they do it, the H1 studies. So uh, if you can observe a wide bandwidth, you can convert the data to the velocity curves. Yeah, but of course, if you have a single telescope, then if you have a pixel, right? You have to move that telescope to different locations in the sky and measure separately like that.
So if anyone has further more questions, you can use the Q&A window as well, or you can straightforwardly unmute and ask, or you can use the chat box option as well. So Also, sir, regarding the sensors that we use for detecting radio signals, certain cosmic events they emit really weak signals. So, how do we detect such weak signals through radio telescopes? So, what sort of sensors that we use?
Yeah, well, to detect weak signals, either we have to collect, for instance, if we have 2 antennas, or we can use 200 antennas. So then, of course, if we increase the number of receivers and spread them out on some place on Earth, then you get more sensitivity. So that's one way of increasing sensitivity, that is to increase the number of receivers. And the other way is, as I mentioned, to observe for over a long period of time and then add the data together. So those are the 2 ways of increasing sensitivity.
That's conclusion of the Q&A session. So we cordially thank our guest speaker for dedicating his important time and giving us a profound and insightful look into an emerging and one of the most interesting technologies that are that are in wide use in astronomy, and which is less talked in countries like Sri Lanka. And so I um, thank again our guest speaker and also all the participants who uh, gave their attention to the lecture and supported us, and also to the members of the Astronomical Society whose contributions led to this event, and also to the treasurer, Dr. Rachita Mendis, and to our department head, Dr. Halinga Bandara, whose contributions also helped us enormously. And I thank all of you for your participation. And hopefully, we will meet again with another interesting topic. And thank you, sir, again for your dedicating your time and giving us such an interesting lecture. Thank you.
Thank you. Bye.